Where? No.
No. You're going to bring up your notes that you're wanting.
I have to talk about this first.
Yep.
I still can. Okay. Hello, students. Today we're going to look at our second lesson from Unit 11.1, which actually is going to begin the notes in more detail. This is going to be over acid-base theories and the properties of acids and bases. So the assignment that was assigned yesterday for today was over the Unit 11.1 Acids and Bases Assignment 1. That would have been due today. Of course, we won't be collecting it at this time. Hang on to it. We will do that at a later time. Again, the answer keys are posted on my Canvas homepage. There's a link there that you should take you right to it so you can check your answers. Please make sure that you do. Just like if you were coming and checking them on the board. So today, again, we're going to start the notes packet in reality on acids and bases. We'll look at acid-base theories and properties. The assignment today, which is entitled Conjugate Acid-Base Pairs, as you can see right here, page 171. That would be due on Monday, March 30th, when we return from spring break, had we been in school. Again, this would have been the lesson for Friday the 20th, had we actually been in session. So just trying to keep things in perspective to kind of keep our schedule as normal as possible. Okay, so here again is our notes for Unit 11.1. You'll need to have these out as we go through this. So historically, chemists have sought to relate the properties of acids and bases to their composition and molecular structure. By 1830, it was evident that all acids contain hydrogen, but as we know from studying organic chemistry and hydrocarbons in particular, that not all hydrogen-containing compounds are classified as acids. So something's amiss there somewhere. In the 1880s, Svante Arrhenius linked acid behavior with the presence of hydrogen ions and base behavior with hydroxide ions, this being in solution. Solutions containing an acid or base conducted an electric current, and thus these substances must release charged particles when they were dissolved in water. Again, the splitting of these compounds due to water's polarity. An Arrhenius acid then is a substance that ionizes in water or splits apart to produce hydrogen ions. So when hydrogen chloride gas is dissolved in water and becomes an aqueous solution, it splits into hydrogen ions and chloride ions, and it's the release of hydrogen ions into the solution that makes that solution have its acidic properties. An Arrhenius base is a substance that ionizes in water to produce hydroxide ions. So when a soluble hydroxide compound, such as sodium hydroxide, is dissolved in water, again, water splits that molecule apart and forms sodium ions and hydroxide ions, and it's the release of hydroxide ions in that solution that gives that solution its basic properties. The Arrhenius concept of acids and bases, although useful, has limitations in that it is restricted to aqueous solutions that only contain hydrogen ions and hydroxide ions directly. About 40 years later, in 1923, Johannes Bronsted and Thomas Lowry expanded the Arrhenius theory and proposed a more general definition of acids and bases. A Bronsted-Lowry acid is any substance that donates a hydrogen ion. And if you think about it, a hydrogen ion is a hydrogen atom that has lost its electron. Remember, a hydrogen atom only has one proton and one electron, so a hydrogen ion is then, in essence, simply a proton. So a Bronsted-Lowry acid is often called a proton donor. In actuality, it's a hydrogen ion donor, but a hydrogen ion proton, they're the same thing. A Bronsted-Lowry base is any substance that accepts a hydrogen ion or proton from another substance and is thus called a proton acceptor. So as we look at these equations here, we're going to introduce some terminology that is very important to our studies of acids and bases. So here we have an acid, hydrochloric acid, reacting with water. And notice an acid in the Bronsted-Lowry definition is a proton donor, all right? A proton donor, which means it gives up a proton to something else. What is formed from this reaction is the hydronium ion. We've not talked about that before. A hydronium ion is basically a hydrogenated water molecule, or a protonated water molecule. And the reason that happens then is because the acid donates its hydrogen ion to water. All right. That's what makes water a base in this reaction. Water is a hydrogen ion or proton acceptor. That in the Lewis-Bronsted definition is a base. So HCl acts as the acid, water acts as the base. When HCl donates that hydrogen ion to water, the hydronium ion is formed. What's left behind of the hydrochloric acid molecule, once it donates that hydrogen ion, is simply the chloride ion. And so here we have introduced two terms over here, conjugate acid and conjugate base. So a conjugate base is the remaining particle of the acid after a proton is released from it. So HCl being the acid and chloride ion being the conjugate base, these two are related by the release or gain of that hydrogen ion. These are called an acid-base pair. All right. Water, which we accepts the hydrogen ion or proton from HCl, when it does that, it forms the hydronium ion. So it forms what is called a conjugate acid. A conjugate acid is what is formed when the base accepts the proton of the hydrogen ion. So water and the hydronium ion, again, are related by this acceptance of a hydrogen ion by water. These two are also called an acid-base pair. An acid-base pair. Notice also in this reaction that we have the double-sided arrow, meaning that this reaction simultaneously goes both in the forward and reverse reactions. As the hydronium ion and chloride ion are being formed by the reaction between HCl and water, at the same time, these two are attracted to one another and react to form the original reactants, HCl and water. So as the forward reaction occurs, simultaneously, the reaction in reverse is also occurring. So this is called a reversible reaction. So here we have basically now showing the reaction going from the opposite way, all right, going from the opposite direction. Since both are occurring at the same time, there's no reason you can't do that. They're both happening anyway. So here we have the hydronium ion labeled as an acid and the chloride ion labeled as a base. Well, here's why. The hydronium ion donates a hydrogen ion or a proton to the chloride ion. Once it does that, HCl is formed, and the hydronium ion, once it releases that hydrogen ion, what's left behind is the water molecule. So again, the hydronium acid acts as the acid, or the hydronium ion acts as the acid because it donates the hydrogen ion. What's left behind that molecule, once it does that, is water. And so here again, these two are an acid-base pair. The chloride ion accepts a hydrogen ion from the hydronium ion. That makes it a base. And once it does that, what's formed when the base accepts that hydrogen ion, which is in this case HCl, is called its conjugate acid. And again, these two are also an acid-base pair. All right, an acid-base pair. So down here we have another example of that. Nitrous acid, HNO2, is the acid. Again, water is the base. So nitrous acid donates a hydrogen ion to water. Once it does that, what's left behind is the conjugate base, the nitrite ions. So here again, these two right here are related by that hydrogen ion. They are an acid-base pair. And here again, water is the base. It accepts the hydrogen ion from HNO2. Once it does that, it forms the hydronium ion, just like it did up here. And those two, again, are also an acid-base pair, with the hydronium ion being water's conjugate acid. Here's another reaction. This involves the ammonium, base ammonia. All right. So where aqueous ammonia reacts with water. So how do we know ammonia is a base? Well, look what happens to it. Remember, a base accepts a hydrogen ion, all right, from an acid. It is obvious or apparent, hopefully, that has happened here because ammonia has become the ammonium ion. It has accepted a proton or a hydrogen ion from the water. So now water is acting as an acid. Up here, it was acting as a base, all right? So ammonia and the ammonium ion, its conjugate acid, those two, again, are an acid-base pair. Water, in this case, has acted, again, as we just said, as an acid because it's now the donator of the hydrogen ion. Water donates this hydrogen ion to ammonia so that it can form the ammonium ion. What's left behind of the water molecule once it donates that hydrogen ion is the hydroxide ion. And so water and the hydroxide ion are an acid-base pair as well, with water being the acid and the hydroxide ion being its conjugate base. So here, water acts as a base. It's a hydrogen ion acceptor. Here, here water acts as an acid. It's a hydrogen ion donator or giver. And so water is kind of a special type substance. We have a term for it. It's called amphoteric, meaning it can act as either an acid or a base. You'll want to remember that term, amphoteric. All right. So we're going to look at some examples here. This erased. So in example 1, it asks us for each of the following acids, write the formula for its conjugate base. Okay, what you got to remember is a conjugate base is what remains from the acid after it's donated a hydrogen ion. So we're going to remove a hydrogen ion from each of these substances, and then what's left behind once we do that would be that substance's conjugate base. So for hydrochloric acid, if you remove a hydrogen ion from it, what's left is simply the chloride ion. So the chloride ion would be the conjugate base of HCl. When you remove the hydrogen ion from nitric acid, what remains then is simply the nitrate ion. Okay, so that would be nitric acid's conjugate base. So here we have sulfurous acid, which has 2 hydrogen ions in it. We're only removing 1. All right, we're only removing 1. And so when we remove that 1 hydrogen ion, what's left is HSO3. Now remember, a hydrogen ion is a positive charge, so this is still going to have a negative charge. We didn't discuss this ion. It looks very similar to the bisulfate ion, but as you might guess, with this being sulfite, it is called the bisulfite ion. We didn't learn that one, but terminology is the same. And water when you remove a hydrogen ion from water, what's left? Well, water contains a hydrogen ion and a hydroxide ion. And so what the remaining particle there would be the hydroxide ion. So again, conjugate base is what's left behind once a hydrogen ion is removed from it. Okay. The next example, for each of the following bases, write the formula for its conjugate acid. Okay, well now a conjugate acid is where a base has accepted a hydrogen ion from an acid. And so the conjugate acid then is what's formed once a hydrogen ion is added to a base. So, a little different here. So now, when we add a hydrogen ion to the bromide ion, which is classified as a base, once it accepts that hydrogen ion, it becomes hydrobromic acid. The -1 and +1 charges cancel, and so this, of course, then is a neutral molecule. When the oxide ion accepts a hydrogen ion, what is formed there? Well, we're going to add a hydrogen ion. This is a charge of +1. This is -2. So it's still going to have a -1 charge, and hopefully you would recognize that is the hydroxide ion. H2PO4. Okay, so again, this is a polyatomic ion that we did not learn. It is actually the ion formed from phosphorus acid once it loses a hydrogen ion. So now we're going to gain that hydrogen ion back. So that would be H3PO4. We add a hydrogen ion to this. Help me, Mr. Jackson. What's the name of that ion? I'm drawing a blank. Is it the diphos? I don't remember. Forgive us, our brains have kind of gone on vacation too. I'll think of it in a minute. When I think of it, or Mr. Jackson will look it up with his trusty phone. I want to say the diphosphate ion, but I'm not 100% sure if that's correct. Did you find it? Of course, you know how you guys know how the Wi-Fi is in my classroom.
Yeah, they're calling it the dihydrogen phosphate.
That's it.
There.
Dihydrogen phosphate ion. Thank
Right.
you. Boy, am I glad you're sitting there.
Oh yeah.
The dihydrogen phosphate ion. Thank you. Yes. Well, that makes sense. Okay.
It does.
Yes. We even have lapses of stupidity. You guys know that, for those of you that have me in class. Anyway, water. When we add a hydrogen ion to water, hopefully we will recognize that that is now the hydronium ion, which again, we're adding a +1 charge to a neutral molecule, which means the ion is going to have a +1 charge to it. So those are conjugate acids, all right? Where a base accepts a hydrogen ion, and then that is the substance that is formed once that happens. Okay, the next example here. Oops, I keep going over there to move up my screen like I've done for years, and now it's right in front of me. Ugh. Old habits are hard to break. And talk about teaching an old dog new tricks. Man, this is as tricky as it gets for me. All right. Example 3, in the following 2 reactions, label acid, base, conjugate acid, and conjugate base with the correct substance listed. All right, so what we got to do is figure out from what we started with here, what happens to it over on the other side. So here we have, oh gosh, help me again. My mind's gone blank. Is that the hydrogen oxalate ion?
Yep.
Is it? Good. I haven't gone totally brain dead. So this is the hydrogen oxalate ion. You guys recognize the oxalate ion, I think. But this is hydrogen oxalate. And over here is the oxalate ion. Well, what happened to this to become this? Well, it had to lose a hydrogen ion, which means that it would qualify it as an acid. Okay? An acid. And then what's left behind from that acid once the hydrogen ion is donated would be its conjugate base. So that would mean that the oxalate ion, C2O4 minus 2, would be its conjugate base. And so these two then would be our acid-base pair. Well, if the hydrogen oxalate ion is an acid, I can pretty well probably guess that water must be the base, since these are acid-base reactions, but let's verify that. Well, a base accepts a hydrogen ion from an acid. Well, look what happened to water. It started out as H2O. It ended up as the hydronium ion, H3O plus 1, which then means it had to accept a hydrogen ion. So that makes water a base. And what is formed from a base when it accepts a hydrogen ion is called its conjugate acid. So that makes the hydronium ion its conjugate acid. And again, those two would be an acid-base pair. So now we have what looks like the same exact reaction, well, the same exact reactants anyway, but now we get two different products. So let's see what happened there. So here we're starting with, again, the hydrogen oxalate ion. Well, what happened to it? Well, over here, it has picked up a hydrogen ion, because you can see it's added another hydrogen, plus it's gone from -1 to neutral, which means it had to pick up a H plus 1 ion. So now the hydrogen oxalate ion is not acting as an acid. It is most definitely acting as a base. And once it accepts that hydrogen ion, it forms oxalic acid, which would then be its conjugate acid. And so those two are an acid-base pair, which then must mean water here must be acting as an acid. Well, if it is, that means it donated a hydrogen ion, which it did, because that's where the hydrogen ion came from to form oxalic acid from the hydrogen oxalate ion. So water here is an acid. And what's left behind from an acid, once it donates a hydrogen ion, is called its conjugate base. That would be the hydroxide ion. And so these two are an acid-base pair. So in the end then, and for these two examples, this shows that both the hydrogen oxalate ion and water can act as either an acid or a base, which makes them both amphoteric. Okay? All right. The third and last acid-base theory we're going to talk about today is from Gilbert Lewis, 1923. That name should ring a bell. All right? Lewis dot structures, Lewis structures. All right, that's him. Not surprisingly, he focused his theory of acids and bases on electrons. Go figure. But now he classified a Lewis acid as an electron pair acceptor. Remember, the Bronsted-Lowry acid is a proton or hydrogen ion donor. This is just the opposite. But remember, a proton has a positive charge, or a hydrogen ion has a positive charge. Electrons, of course, have a negative charge, so it kind of makes sense that this thing is reversed around. A Lewis acid then is an electron pair acceptor, while a Lewis base is an electron pair donor. Right? Again, just the opposite of Bronsted-Lowry. There I go again. This theory expanded the definition of acids and bases even further to include solutions that don't involve hydrogen ions or hydroxide ions. So here on the next page here, we're showing boron trifluoride as an acid and ammonia as a base. Well, we talked about, but here, these are gases now. These are not in solution, okay? In fact, these are all gases. And so we've identified ammonia as a Bronsted-Lowry base when it's in solution. We can also identify it as a Lewis base based on his definition when it exists as a gas. This is really helpful, this definition, when you're talking about substances that exhibit acidic or basic properties, but they're not in solution. But when put in solution, they do. This helps explain that. So how do we see this? Well, we use Lewis structures. Surprise, surprise. All right, so if we look at boron trifluoride, remember boron is an exception to the octet rule. It only has 6 valence electrons. Remember, it's a contracted octet. Looks like that, trigonal planar. And then ammonia is a trigonal pyramidal. Draw it this way so we can see it a little better. Well, right here is that pair of electrons, all right, which it will then donate to boron so that it can achieve its octet, all right? Remember, that's a coordinate covalent bond. If you remember that from when we were doing bonding, well, that makes this a Lewis base, right? An electron pair acceptor. So when it's all said and done, here is our molecule that we formed right here, showing that coordinate covalent bond there. So NH3, again, being an electron pair donor, makes it a base under the Lewis definition, and boron trifluoride, being the electron pair acceptor, makes it a Lewis acid under this definition. And again, when these compounds are in solution and exhibit those acidic and basic properties, which wouldn't be explained other than through this theory. So it can be very helpful. All right. Here are some properties of acids and bases in general. These were actually on your assignment that you worked on yesterday. We'll talk about these for just a minute. Acidic things give foods and drinks a tart or sour taste. So think of anything you've eaten or drank that has a sour, sweet tart. Lemons, limes, oranges to some degree, tomatoes. Vinegar is quite sour. All of those things are acidic. Will conduct an electric current because, remember, these compounds are electrolytes. Right? When dissolved in water, they split and form positive and negatively charged ions. Acids react with metals to produce a salt and hydrogen gas. So we've talked about these in our earlier discussion of reactions, single replacement here. React with metallic oxides to produce a salt and water. Will neutralize a base to produce a salt and water. Of course, that's an acid-base neutralization reaction. Will affect certain indicators. Will turn blue litmus paper to red, or red litmus paper will remain red. All right. So I think we've worked with litmus paper before. If we haven't, we probably have in middle school. But we'll be looking at this again when we do our next lab. But acids are red, all right? So they either turn a blue paper red or red paper will stay red, all right? One or the other. Bases, properties of bases. Aqueous solutions that are termed basic have a bitter taste. Might remember from Chem 1 when we had you taste some chalk. What was that? Powdered chalk? Cocoa powder, yes. Very bitter, all right? Definitely basic. Feel slippery to the touch. Well, geez. Hand sanitizer, soap, bleach. You ever got bleach on your hands? You know it's real slick. All of those things are basic, all right? It's also an electrolyte, so it'll conduct an electric current. Will neutralize an acid in an acid-base neutralization reaction, and will affect certain indicators will turn red litmus paper to blue, or blue litmus paper will remain blue. You might remember too when we were doing, let's see, we had a lab not too long ago. Oh, I know what it was. When we reacted in our reactions lab, reacted a metal oxide with water, which gives you a base, and we had to use pH paper to look at at what its pH was. And if you remember, it turned extremely dark blue, which meant that it was basic. Basically the same principle here with blue litmus paper, or red litmus paper turning into blue. So I think that's all we have for today. You should be able to now complete your conjugate acid base pair assignment. As we said in the do nows, that'll be due tomorrow. And then again, as I've said several times, the answer keys to all these assignments, as well as the notes, are also posted on my Canvas page. On the front page, on the home page, you'll be able to link to them from there. So, signing off for today. We'll catch you on the next lesson. Remember, this was technically our last lesson for this current week, last week before spring break. So our next lesson would be the first day we return from spring break. So till then, see you later. Enjoy your break. Signing off.